right, so I'm audible, am I? Yes. Okay, very well. So yeah, let me start off this kickoff meeting by thanking the organizers for actually inviting me and all of us from all over the world here. And you shall be congratulated by establishing your quantum center. It's a timely business. Timely because it's quantum physics gets inspired by lots of neighboring disciplines like mathematics, computer science, and so on and so forth. But most importantly, quantum physics is inspiring neighboring disciplines like engineering science, and especially in a young place, like young university, building up faculty. This can be really a pivotal point in how the research strategy of the university is unfolding. And by making that center, you make sure that quantum has its part in it. Actually, what I'm going to tell you today, this morning, in the next, say, 35 minutes or so, is very much inspired by stressing the interdisciplinary character of quantum physics. I'm briefly explaining you the tools we're working with when we do quantum sensing on the nanoscale, but I mostly dwell on actually where the applications are in different parts of science. So what I'm talking about actually is a pretty young area in quantum physics where we try, or where we are using solid-state systems, specific solid-state systems, to do microscopy, spectroscopy on length scales and with sensitivities which are unprecedented. And also here in Israel, there is a growing young community playing working on the system. Nadav, who is somehow in the flooding of discussions about those systems, and there are other places where this is done too. Actually, the nanoscale sensing we are doing has already made quite an impact in different areas of science. For example, in solid-state physics, where people look at the physics, at the behavior of low-dimensional electron systems, and I'm going to exemplify what we do there in a couple of minutes. But it's not only solid-state physics, for example, also magnetism, it's also biomedical analytics, right? The way we do our quantum sensing actually lends itself to being applied to problems in life science. And also now industry is starting to use our tools. For example, hard disk drive industry, which has a hard time actually to come up and construct the next and over next generation of write-add physics, to increase storage density in hard disk drives. And so now some of our instruments, some of our tools are used by hard disk drive industry, Seagate, for example, Toshiba, to construct and optimize forthcoming hard drives. And if I have time, I'll talk about that in a second. Now, the physics of all of that is actually, or say the selection of tools we use is actually the criteria for the selection of tools, I should say, and we're using is pretty easy to see. So we are by heart solid-state physicists. That is, we work with condensed matter systems, and in particular in this case, those which have a wide bandgap, a couple of electron volts, so that by doping you can define atom-like states within the bandgap of that material. And then we watch out that whatever you dope into the solids fulfills two criteria. On the one hand, it has a strongly allowed optical transition with an energy on the order of electron volts, so in the visible part of the spectrum, where we can use very efficient laser sources, but also very efficient detectors. These optical transitions we just use as a readout for the sensors, and I'm going to explain. Doing optical readout has, from the technical side, has a benefit that it's very easy to come to fundamental noise, that is short noise performance. Very difficult to do, for example, for electronic readout, but very easy for optics readout. Now, the sensing in itself, the measurement of quantities we are interested in, is not done by the optics, but it's done by spin levels those systems have attacked. Right? So what we do basically is we do a precision measurement of spin levels which are built into our sensor systems. That could be electron or nuclear Zeeman levels. And we can read out those, this energy splitting here, say between spin up and spin down of a paramagnetic dopant with a precision down to femtoelectron volts, right? And it's this femtoelectron volts over this electron volts, so 10 to the minus 15, which somehow gives you a feeling for the precision level at which we are working with. So these are our sensor levels. Now, first thing to do is, and I'm going to motivate why we are doing it the way we're doing it. By the way, those of you knowing, having a background in atom optics, will realize that similar schemes are used, for example, in atom clocks, right, where the clock transition would be somewhere down here. All right, so what are the solid-state systems we're working with? Well, it's first of all wide-bandgap semiconductors, carbon-based material like diamond, silicon carbide, but also these materials here, yttrium aluminum garnet, which basically is the material where these laser pointers, especially these green ones, get their photons from. And then we dope it, for example, these yttrium aluminum garnet, we dope it with rare earth or transition metal ions, cerium, praseodymium, europium, and so forth. And these other solid-state materials we just dope by, for example, punching holes in it or implanting impurities like the nitrogen here in this and well, all of them work similarly. They have their pros and cons, and we'll just concentrate on this one here for the sake of simplicity. So I'm just going to talk about these defects in diamond. All right. So the sensor readout actually is pretty simple. So these diamond defects, they comprise this nitrogen plus vacancy, and that exactly makes a strongly allowed optical transition at around 2 electron volts in the bandgap of diamond, which is on the order of 5.5 electron volts, right? So, and actually these transitions are mixed in the bandgap, and that gives you a very efficient shelving against, for example, photoionization processes or other degrees of freedom in the solid, like phonons or other quasi-particles. There is strong photoluminescence or fluorescence, and here you see the image of a single defect in such a diamond being taken with a fairly standard instrument. And now it's next to these optical transitions, you have these spin transitions, which in this case is an S1 system. So you have 2 unpaired electron spins, which when you put that in a magnetic field, you get 3 sublevels, +1, times up to 0, and -1. And these are the sensor levels. So by a precision measurement of that splitting here, actually you gain sensitivity towards a kind of a whole wealth of parameters, which I'm going to show you in a minute. Now the readout is pretty simple to see. It's just this sublevel here taking place in optical excitation and emission. So whenever you use magnetic dipolar transitions here, the sensor basically gets dark, and this is your readout. So if I now plot here the fluorescence as a function of this frequency, I see this dip here, and that is exactly the measure of the delta E here, which I try to make as precise as possible.
I don't understand. In diamond, there's an energy gap between the n equals 0 state, which is the ground state, and the n equals plus and minus states, which are degenerate at 0 magnetic field.
Absolutely.
So I don't understand this, the lower part of this figure.
Well, this is, here I assume that there is a magnetic field present. So there is something which breaks the degeneracy as you are saying, right? So you have spin up.
It's a very large number.
Well, it's not broad to scale, that's right. So okay, down here, this splitting typically is on the order of micro-electron volts, and this is electron volts, right? So it's drawn simply out of scale. Okay. Well, one reason to choose this material, or also silicon carbide, for example, is its low spin orbit coupling, giving the spin relaxation times on the order of milliseconds at room temperature. And it's always instructive to compare them to other systems in the field, like gallium arsenide, or if you put phosphorus and silicon, same story. Here, typically, these times are on the order of some tens or, say, 100 microseconds at 2 Kelvin. Right? And this is one motivation for us, is low spin-orbit coupling to work with that material. All right, you can also pump that spin here up and down, look at Rabi oscillations, which is an indication that you have good coherence times here already. And that's of course important for precision sensing. Now the way we typically do, the quantities we can measure is on the one hand magnetic field, right, that's trivial. You have an electron spin, so you have a Zeeman interaction, and that gives you sensitivity to magnetic field. It's also, you can measure electric fields. There is tiny spin orbit coupling, but that's good enough actually to measure electric fields via the spin split link. And you can also measure temperature and force just by spin phonon interaction, which is small but measurable. Yes?
Can you tell me what your energisticity would affect the magnetic field or electric field?
If I would work.
So you see it like a shift in energy?
Yes, yes.
Is it due to electric field?
That's a good question. Well, the kind of general answer is the overall symmetry of the Hamiltonian given to electric field shifts and Zeeman shifts is different. So by playing around, actually, for example, by making measurements at zero magnetic field, you basically have a Hamiltonian which is maximally sensitive to electric fields. So if you want to see the electric field sensitivity, and you really want to be sure that you measure electric field, the best way is to slightly change the magnetic field and look at the magnitude of the effect. So once again, the symmetry of the electric field Hamiltonian is different, and this is what you can play around with in your sensing scheme. All right, if I have time, I'll come a bit to how one measures temperature, but in a nutshell, it's just spin phonon interaction, which we make use of here, which we can control and which we know better. All right, as typically well, this is a menu, right? So I've shown you a bit about magnetic field imaging and measurement, and a bit about temperature measurements, and I'm concluding with an outlook. All right, so let's start. So typically, the measurements we do in a way which is almost always done in precision measurements. We actually use Ramsey fringes. That is, we use the temporal evolution of the wave function we use for measurement to determine the quantity we want to measure. So, for example, if you want to measure magnetic fields, right? We just start our experiment and let the wave function evolve in the magnetic field, and then at some point we measure the wave function. Specifically for the spin, right, what we do is we start the experiment at t0, and then we let the spin precess in the magnetic field, and we measure the angle over which it has precessed after some time t. And that is related to the magnetic field. We want to measure by constants or fundamental constants. And this is how actually we do the experiment. Now delta phi is getting more precise if t is getting larger. Right? And t finally is determined, or it's limited, by the dephasing time, by the time over which we can tell which angle the spin has precessed. And in diamond, for example, but also in silicon carbide, it's only almost milliseconds. These are record values in solids, and this is what makes it a good sensor, right? This is what makes it an outstanding solid-state sensor. Okay, so now you can actually define the sensitivity, which is 1 over square root of this time, multiplied by a couple of constancies. And this C here is the signal to noise in the radio. And at the field sensitivity, there's actually a square root of hertz missing here. We measure for a signal defect is on the order of 10 nanotesla per square root of hertz. And that's the field of a single nuclear spin at a few nanometer distance. Which is a good field sensitivity. I would say it's not outstanding, but as the sensor can be very small, in the end you can make it a real remarkable sensor. Now, for sake of comparison, what you can do is actually to increase sensitivity is rather than working with a single defect, you can work with a whole bunch, say n defects. And if you have a thermal ensemble, the signal to noise actually in your readout improves sensitivity.
But would you then need to work T2 stars?
Well, this is that's a very good remark. I'm kind of cheating here because basically I should give this sensitivity here in a certain bandwidth. And what I'm plotting here is, or what I was calculating here, is a sensitivity at E-field frequencies, say above 100 hertz or say 100 hertz or so, right? This is why I'm not worrying about T2 star. All right. So if I now take an ensemble, thermal ensemble, plot magnetic field sensitivity over measurement time, this would be the square root of hertz kind of pivotal point. Then I end up with something like picotesla. At least that's where we were a year ago. Now we are down at 200 femtosecond. And just to compare, if you take an atom vapor, not a super duper system, but a standard atom vapor system, then you are at 1 order of 10 femtosecond square root of hertz. However, at very much larger volumes, right? In a cubic centimeter, and here we talk about a few cubic micrometers. So whenever you have a say a measurement challenge where proximity plays a role and where your quantity is decaying off as a function of distance, then this is getting the good system to work with. And one kind of funny example is measuring the magnetic field of axons, right? Axons are nerve cells. This is what makes your limbs moving. And from a physicist's point of view, this is nothing but a current wire, because there are ions pumped across the cell membrane. And so there's current flowing, and this generates a magnetic field. And the magnetic field decays off as 1 over r, right? So you barely come close. And this is an axon here from a frog, from this frog. And actually, we were doing the experiments in Australia because there is a certain abundancy of these pretty large frogs, with these pretty large axons. The diamond you hardly can see. It's a small piece of diamond right below, and here you see the microscope objective reading out the optics. Right? Proximity is important there because you want to go as close as possible to the wire. And this is actually the magnetic field measured versus time. If you remember your bio classes, actually action potentials across axons, they have this very characteristic time dependence where you have this kind of positive spike here, and then you have a negative going part here. So this, that's a good kind of fingerprint for you actually measuring the axon magnetic fields. You see the field is not very small, it's on the order of nanotesla also. And this is only the second time this has been measured. First time was with squids in the 80s, where here the scale was picotesla because squids are larger, you have a larger standoff distance, and you need to have a much better sensitivity.
Jorg, if you can just raise the microphone a little bit because it's a little bit.
Raise my voice. Is that better? Is that better? Is that better?
So it looks like this is not an in situ measurement, right?
Absolutely.
But you show us like something which looks like nature.
Oh yes. Well, once again, proximity counts. So unfortunately, you need to take the axon out of the frog. Right?
But the frog is still alive.
No. Don't let us go into the details of that. Anyway,
It's like a natural signal in biology.
Yes, absolutely. So this is the axon. The axon is alive. The frog, unfortunately, not. And what you need to do is you need to activate the axon, and that is what you do here with these electrodes. Right? And then there is an action potential propagating. Actually, it's a space-time signal propagating across the axon. And here at that point, you catch that. And there's very nice parallel work by Ron Wordsworth, and he's doing similar things on the signal. So there is actually hope that this turns out into a real viable tooling biology. But let's move on to physics. So people have made it an art putting these defects, for example, on the tip of these kind of stylus thing, right? So that's a single defect here at the tip of that. Of such a structure. It was actually Ami Jacobi and Patrick Valentinsky pioneering that. And then what you can do is you can scan across that tip, across some structure. Once again, it's a biostructure. This is a protein, specific protein which plays a role in mitosis. And here what we have done is we have put an electron spin at a certain part of the protein. And then you have dipole-dipole interaction between that electron spin here and that here. And that allows you to measure the magnetic field as a function of location. So you have lots of those proteins on the surface. And whenever you see a bump here, you see that there is magnetic dipole interaction. And once again, I'm flashing through that very quickly. What we did in this paper here is we were then parking the tip here and measuring the dynamics actually of that part of the protein by looking at the temporal changes of the distance between these two. And with that, you get really a unique insight into the protein dynamics in that system. That's, by the way, done at room temperature, so there is some biological relevance, and people wanted to know actually how mobile the protein or dynamic is. All right. But if it comes to imaging, and if it comes to application of imaging of magnetic fields, it is not this scanning probe kind of configuration which is actually abundant in applications. The most abundant magnetometer imaging magnetic field device is this thing, right? That's an MRI, magnetic resonance imaging machine, and I'm not sure if you have one in Bar-Ilan around here. You haven't met it?
In
Oh, okay. Well, anyway, I'm pretty sure within a radius of like 30 kilometers or so, you find one or two of these machines, because they are the key instrument in actually measuring soft tissue in medical diagnosis. And what it does is actually it measures the magnetic moment of proton spins, of protons in water, because our body is mostly made out of water. And it measures, it encodes, spatially encodes the signal of the magnetic moment of those protons by applying magnetic field gradients by these gradient points. Now, in our experiments, we were somehow trying to mimic basically these kind of machines, because they are most widely used across all kinds of science, not only medicine. And the first thing we were asking ourselves if with our sensor we can actually see the tiny magnetic moment of protons, right? Proton has a factor of 1,000 smaller magnetic moment, so sensitivity is getting an issue. And what we were doing is we were just putting a drop of a liquid on top of a diamond surface, with the defect being very close to the surface, like a few nanometers. And if you do that, you actually see the magnetic moment, in this case of proton strings, which were in a hydrocarbon oil. And if you remove that, right, if you deuterate what you put on, then the signal disappears, because deuterons have an entirely different magnetic moment. And if you put it back on, you see the signal coming back up again. Right? The overall magnetic field, by the way, if you are that close, is not that small. It's on the order of, say, half a microtesla. And this half of a microtesla magnetic field, in this case, is generated by around 100 proton strings.
Is this in the constant magnetic?
This is in the constant magnetic field. There you go. Well, it's a good question. From the top of my head, I would say it's on the order of 3,000-4,000, so 0.3 Tesla, so rather low magnetic field actually for this kind of experiments. All right. And meanwhile, people have taken this actually down to almost a single nuclear spin. All right, so let's compare that. So this is what this probably you have here at Bar-Ilan. If you have a chemistry department or a structural biology, this is actually this is their standard instrument. It's a nuclear magnetic resonance machine. It takes something like 10 to 15 nuclear spins to generate a signal here. The reason is that actually you measure magnetization by the current or the voltage it induces, the temperature changing magnetic field it induces in pickup points. Sensitivity of those machines increases as the square of the magnetic field induced. And this is why these machines get bigger and bigger, meanwhile, they fill these rooms. So if you compare this sensitivity here and ours, we are certainly way better, right? With a fraction, an epsilon of the effort people take there. But it's actually not sensitivity which makes these instruments, the standard instruments in that field. It's spectral resolution. Now, nuclear spins actually are a fantastic measure of the electron environment of the compound you are using. If you are in solid-state physics, say superconductivity, actually electrons and nuclear spins are the best measure of the Cooper pair density and distribution in your solids. And they are actually extremely good measure, for example, in the electron distribution in molecules. So what they measure is the electron density, because the electron density determines the local magnetic field, right? You have a diamagnetic shielding. If you put an electron cloud into a magnetic field, then this tries to shield off the magnetic field, and the shielding efficiency depends on the square of the electron wavefront. So if you want to measure electronic distributions, you use nuclear spins. And because electron distribution in a molecule, even though you're looking at one and the same nuclear spin, is different in different parts, what you get here is a fingerprint actually of the molecular electronic wavefront. The effects are tiny. Yeah.
It's actually the same as night shift.
It is, well, night shift is for an electron gas, right? It's a physics, it's a bit slightly different, but it's, well, in the end, the effect is the same, right? You have a local magnetic field which depends on, say, electron density, and then you are in. But the point is the differences are tiny, right? And this frequency scale here is 100 Hertz at a background field of around 1 gigahertz. Right, so the spectral resolution you need is 10 to the minus. Over the last, say, 2 years, we and others were fighting getting actually our method to that spectral resolution. And the way we're doing it is rather than using the electron spin in itself, we use nuclear spin quantum memories to actually enhance resolution. So one of the assets of that system here is that that diamond is made up out of carbon, and carbon is 1% carbon-13. So it's nuclear, there are nuclear spins in there. And this 1% actually gives you a diluted gas of nuclear spins around the electron spin. And if you look at the center, and if you measure an electron spin, and if you measure the coupling with its environment, so there is no sample for the moment, then you see that there are different couplings here. These are all hyperfine couplings of the electron spin to different nuclear spins. And for example, for that particular one here, we found a set of 7 to 8 nuclear spins, all with specific couplings. And we use those as quantum memory because they have extremely good relaxation properties. So the T1 time of those nuclear spins here at room temperature is on the order of 4 minutes. T2 time is 3 seconds. And we make use of these very long storage times actually to enhance not the sensitivity but the spectral resolution of our sensor. All right, so dynamics is so slow that you can actually follow the spin flip, the quantum trajectory of these nuclear spins in real time. All right, so let me just go through how we do that. So we use the electron spin as a sensor to measure the magnetic field we want to measure, right, as we did it before. And here I'm exemplifying what we're doing by adding one nuclear spin here. And we add here one nuclear spin as a memory. The memory is just made to actually allow us to measure the magnetic field we want to sense here for a longer time. So we enhance the T2 time of our sensor. And we do this in the following way. We start out with an entanglement sequence here between electron and memory, so that at the end of the pulse here, we end up with this entangled state. Then we actually have this state here requiring phase in the quantity we want to measure, say the field of nuclear spins. So that at this point here, we have this phase, which is actually the quantity we want to sense. Then we apply another gate here to disentangle electron and nuclear spins. So by this gate here, the phase we have measured in the correlated electron and nuclear spin state is now entirely in the memory, right? So we factor out, so to say, the electron spin. Then we wait for some time t, and this time t can now be very long. It can be seconds or long, or even minutes, depending on how you operate your memory. And then we redo the measurement. That is, we once again do a phase measurement, and we then measure in how far the phase we have measured here has changed. So basically, it's a kind of a correlation that we do. And by that, basically, right, we can measure for an extended time t, and as you are probably aware, the more precise you measure the state of time, the better the expected resolution is getting. Now, we not only do this with one nuclear spin, but we do it with a whole bunch of nuclear spins. So what I'm doing here is I'm plotting phi, and I symbolize the evolution of the phase of the electron spin in the quantum magnetic field we want to measure. And what we do is we store, say, the phase at some point tau in carbon 13 nuclear spin 1, and we take the second carbon 13 nuclear spin, store the phase here, then we once again store another phase here, and yet another phase here. And if you plot now the Fisher information on the phase you have measured as a function of the nuclear spin qubits, and you compare it, now you compare the sensitivity you have acquired here with the standard quantum limit, which is the bluish curve here in this plot, and the Heisenberg limit, that's the reddish curve here, then you end up with an improved sensitivity, which is not quite Heisenberg scaling, but it's much better than the standard quantum limit. And by this, we do two things. We increase the spectral resolution of our magnetometer, and we increase the sensitivity also. And if you cook that up, if you use all that these recipes together, then lo and behold, you really come up with pretty high and very sensitive NMR detection. But this is one experiment I'm showing here. Here we were measuring the chemical shift, or as we refer, night shift of these fluoride nuclear spins. These orange pinkish ones here, they all have one frequency, which is this one here, and this one here has a separate frequency you see here. So the resolution we get is on the order of, say, 100 hertz or 200 hertz. Good enough actually to really use this as a tool for chemical structure analysis. Now, there is one final step left before I'm almost concluding. We want to make this an imaging technique, right? This is what we were starting out with. And this is what I'm going to show you now. And to make it an imaging technique, what we do is we take now a sensor, which is not just a single defect, but which is a thin layer of defects, homogeneously distributed, very close to the surface of a whole chip, of a whole diamond chip. We put the sample on top, and we image now not a single defect, but a whole bunch of defects in a wide field fashion onto a CCD in a more maybe restrictive way. So what we do is we have now a whole layer of NV centers. We put our specimen on top, and we get spatial resolution by doing a wide field image of specific parts of the chip onto a CCD. So that's the kind of image you can expect to see. And to exemplify that, what we did is, in the test experiment, we were putting a cell, so once again a biostructure, which we were labeling with a fluorescent dye on the cell membrane. And then we were using fluorescent microscopy just to show the perimeter of the cell. And at the same time, we were using MRI imaging, and we were specifically imaging the phosphoryl hair groups. So this is a phospholipid bilayer, and it has phosphorus in its outer perimeter. And we were using that image to actually measure the cell parameter. And that's what you see here. Right? Both images look alike. That's actually what they should do. Both have a pretty bad signal to noise, especially this one here. But just to show you, this is the first MRI image being taken now almost 40 years ago. It looks pretty similar than what you see here, although it's an entirely different specimen. This is a human body cut at the apical valley, and the length scales are of course entirely different. Right? This is a few microns here, and this is of course here all signal to noise system, right? And as I've improved signal to noise here, we hope to improve signal to noise here. And then it's going to be really an absolutely usable tool. And it's a new way, by the way, to do optical microscopy, because it's label-free and chemically specific. All right, so I'm concluding off with a physics example. So one thing we were doing is we were trying to measure the magnetic moment of a boron nitride layer. There is very nice work also from Misha and his guys in Harvard doing similar things. And I'm showing you the twist we were taking on this approach. So what we were trying to do is we were trying to use a signal defect center to measure the magnetic moment of this 2D layer. Boron nitride is, well, it's composed out of boron nitride, obviously, and it's a nuclear spin system. So boron and nitride only have 2 nuclear spin isotopes. So this is basically a 2-dimensional lattice of nuclear spins. They show up in an NMR spectrum. That's a pretty murky one. It's the first one we were taking. And it's these 3 lines here being indicative to the boron nuclear spin, which is 3-half. That gives you these 3 resonant lines. All right. So what we are trying to do is we are trying to make this a 2-dimensional simulator for interacting magnetic dipole moments. And the idea of actually what to do with that comes from a paper from Martin Plenio in Fedor for almost 5 years back. And the idea is pretty simple. If you apply a strong magnetic field, and I think I should speed up, right? Not to run out of time. So if you apply a strong magnetic field, then you can actually render this 2-dimensional parity.
Maybe some of this works.
This doesn't work. All right. So so if you apply a strong magnetic field, then basically you render this interacting set of nuclear spins to an XXY, an XXZ kind of model. And basically what that means is if you have a magnetic field, in this case an in-plane magnetic field, the magnetic dipole interaction of all the spins among each other can be changed, can be efficiently changed. And this change is actually given by this factor G here, the magnitude of which you can change by changing the in-plane field orientation. And you can, by proper in-plane field orientation, you can make the system ferromagnetic when G is getting smaller than 0, or you can make it antiferromagnetic when it's getting larger than 0. So that's basically the idea of that system, of that approach. Well, there is one caveat here. Well, first of all, I mean, changing the field orientation is pretty easy to do, right? It seems to be a very readily doable system. The caveat is that the interaction strength here is very small. It's on the order of 20 kilohertz. So you would need to have a base temperature of 30 K to have a very well defined ground state of your Hamiltonian of the system, right? And 30 microkelvin to achieve in a solid state system is quite a bit. Well, for us, this is getting doable because we can use our sensor to measure magnetic moments. but we can also use it to cool magnetic poles. And this goes by actually exchanging spin between the electron and the nuclear spin. It's called dynamic nuclear spin polarization. One thing you need to fulfill is that you need to bring the electron and the nuclear spin to the same energy scale to have an efficient flow actually of spin order from here to here. And there are tricks known how to do this, which are around now in the community. And cutting a long story short, if you apply these tricks, like these DMP sequences for the expert, and you look basically at the spin temperature of your boron nitride as a function of time, and this is what you see here, you see that you can achieve a very high spin polarization of the boron nitride, basically being on the order of 10 microkelvin. That's slightly lower than the order temperature we need. It's not as low as you would wish it to be, but nevertheless, this allows us actually, and this is my concluding transparency, to do quantum simulation. And this is a numerical simulation from Martin in his paper, where he's showing the phase transition between a ferromagnetic and a 1D antiferromagnetic chain by just changing the orientation of the magnetic field in plane here. And this is the simulations we do. So that's supposed to be our 1D antiferromagnetic chain, and this is supposed to be the phase transition we want to measure. Well, and if you, at least it occurs at the right order of magnitude, which is given by the ratio between K1 and K2 here. It's not very sharp because the temperature of our spin system is too high still, but at least you see an indication of that phase transition. All right, so with that, I'm at the end of my talk. This precision temperature sensing, I think we need to skip anyway, not surprisingly. And I'm concluding with an outlook. I was exemplifying everything we were doing by measuring magnetic fields. But as I was stressing in the beginning, it's not only magnetic fields, it's electric fields, it's force, rotation, maybe even gravitation, which we can access by these sensors. And the tricks you have seen actually all apply and can be applied to, in the end, achieve pretty good quantum sensing with these systems. All right, so with that, I'm at the end of my talk. This is a group in Stuttgart. We have collaborations with a lot of people all across the world, and we get money from different sources. Until a couple of months ago, we even got some money from the US, from Africa. Well, I'd like to thank those people, and I thank you for your attention. Thank you.
We have time for a couple of short questions.
What's the actual temperature in the boron nitride?
The experimental temperature, the environment, 300 K. Yeah, it's a room temperature experiment. While cooling down on this temperature scale doesn't help you a lot, unless it expands your cooling mechanism itself.
So you started by saying that you have several materials, several platforms that focus on these centers.
Yes.
So are there advantages to other platforms, or is any center the best?
Well, it's all in, there are two key components which you need to have. One is that the spin in your system is good, and the spin in all of those systems is good. Second thing is that you need to control the doping almost with atomic or at least nanoscale precision. And this is best done actually in silicon carbide, not in diamond. So my prediction is in the coming years it might very well be that silicon carbide is replacing diamond in these systems. But otherwise, in these applications, but otherwise the systems are almost identical. With respect to relaxation times, dephasing times, and so on and so forth.
We showed the scaling of the spectral resolution.
Yes.
With the number of scales that you are
Yes.
coupling.
Mm-hmm.
And it seemed to me to be exponentially growing. There was a semi-log scale.
Yeah, when it's square root, it's actually scaled with the standard quantum limit. It's a square root of n scaling, very, very precisely.
And
Yeah.
how much you lose, if any, by decoupling your measurement scale and letting it sit and accumulate just a phase without the interaction? Is it a
Yes.
factor of 2 or is it more?
But this is actually, it's the scaling you have seen there is for independent particles. So the spins are not interacting with one another. You're right. If they would be, then the physics is entirely changing, right? Then you would go through, by excitation, you would go through quasi-entangled squeeze states and so on and so forth, right? But this is not the case here. This is really just quite trivial square root of n scaling.
Okay, let's thank the speaker again.